So that means, for example, if I say unit step function, if you sum up together the unit step function u of n, okay, u of n. So u of n, if you sum up this u of n from n equal to 1 to infinity. So if you take the summation of this u of n, then if you go on adding, the value is 1 for n equal to 1, is value is 1, for n equal to its value is 1 also. So if you go on adding this one value from n equal to 1 to infinity, so that leads to infinity. Okay, so that means this square unit step function is not absolute summable, right? But if you take the square of that function, u square n, so u square n, so that means the amplitude is 1, so 1 square, again it is 1. So if you go on adding from n equal to 1 to infinity, so adding 1 upon 1 upon 1, so again that will take to infinity also, right? So that means u of n is neither absolute summable nor square summable. Then there should not be a Fourier transform exist for u of n, isn't it? As it is not satisfying the Dirichlet condition. Okay. Then another example is cosine function. Okay, cosine n omega 0 or sine n omega 0, or I can take e to the power j n omega 0. Okay, so these functions also, if you go on adding these functions from n equal to 1 to infinity, so again that leads to infinite value. So that means it is not absolutely summable. Okay, so if you take the square of this function, that means cos square n omega 0, sine square n omega 0, then also that integration or summation that leads to infinity. Again, that is not summable in square form also. So it is not a square summable. Okay, so if it is neither square summable nor absolute summable, then it doesn't satisfy the Dirichlet condition. That means the Fourier transform doesn't exist. But there is a Fourier transform exists for these signals also. That is the most tricky part. Okay, so most important part. So like if there is no like if the Dirichlet condition doesn't satisfy for absolute summable or square summable, then we can find out the Fourier transform of these kind of signals by putting a mathematical trick. Okay, so what is the mathematical trick? So we'll introduce a delta function. Okay, we introduce a delta function or analog delta function. So that means integration 0, integration of del omega d omega equal to 1. So that is the delta function. Okay, so direct delta function. So we'll introduce a direct delta function to find out the Fourier transform of those signals which are neither absolutely summable nor square summable. Okay, so that means we'll represent the Fourier transform of these particular signals with the help of a delta function, right? Okay, so I'll give an example later on. So how do you represent the Fourier transform of this category of signals like which are not summable, okay, absolutely or square summable, right? So that means we'll introduce delta functions in the Fourier transform representation of this kind of signals, right? Okay, so except this, if at all, if any signal which is not satisfying Dirichlet condition, then it is difficult to find out its Fourier transform representation. Okay, so this is one of the most important and vital part of the Fourier transform representation. Okay, so it should be absolutely convergence. If it is not absolutely convergence, then we cannot get we can't get the Fourier transform of the signal, right? So now, if I ask to find out the Fourier transform of delta function, okay, delta signal, delta n. So if I ask x of n equal to delta n, then find out its Fourier transform. Sorry. Then find out its Fourier transform. So what is the answer? Can someone tell me? What is the answer? If x of n equal to delta n. Praveen Kumar, what is your answer? Praveen Kumar Reddy, do you listen me?
Sir, good afternoon, sir.
Good afternoon. Praveen, answer. What is your answer for the Fourier transform of delta function, delta n? X of n equal to delta n, then how we find the Fourier transform of that?
We can use this discrete time Fourier transform, sir.
Fourier transform. Yes, very good. Then find out.
That is, and find out directly like x of n is equals to
summation n equal to minus infinity delta n to the power j n
x n into e power minus j omega n.
Yeah. Okay. Then evaluate it.
Yes, sir.
And you know delta function. What is the property of delta function?
It will be unity at n, when n is 0.
0, and the rest of the time it is 0.
0.
Right? Yeah. So then you have to put n equal to 0. So at n equal to 0, its value is 1, and then delta n delta 0 is 1, and e to the power minus j 0 into omega. 1. So e to the power 0 also 1. So 1 into 1 is 1, and the rest of the time, if you put the rest of the n signal, so delta n will be ultimately it will give you 0. So it is value is the summation 1. Okay. So that means the Fourier transform of delta function is 1. Okay. This is very, very important observation. Okay. So when you say delta function, the Fourier transform of delta function is 1, then what is consequence? What conclusion you can draw? So if you represent, if you know the delta function is one of the most vital elementary function for any kind of signal and system analysis. Okay, when you go on system analysis, then this delta function is play a very vital role. What is that? What is that role? So a delta function, if I give an input to the LTI system, then that gives me output as the impulse response. Okay, if I give input as impulse, then what is the response of the LTI system is called the impulse response. That is your h of n. So if you find h of n, that means you are completely known about the system itself, LTI system itself. That means we can characterize the system. Okay, characterize the system means like how it will behave to other kind of frequencies. Okay, how it will be whether it will be a stable system or unstable system, or causal system or non-causal system. These are the behavior of the LTI system that you can analyze if you know. Yeah, if you know the impulse response of the system, right? Now, the frequency response of the linear time invariant system, that LTI system, is considered as the Fourier transform of a system's impulse response. Are you getting my point?
Sir, can you repeat?
So all of you note it down. This statement is very, very important statement. We can say the frequency response of a linear time invariant system, LTI system, can be considered as the Fourier transform of the system impulse response. Okay. So that means how the system is going to behave to all other rest of the frequency. Okay, any frequency, any signal of certain frequency, that can be characterized if I have the that is nothing what we call frequency response. Okay, so how the signal LTS system is going to respond to the signal of certain frequency. Okay, so how can represent this one? By looking at the Fourier transform of the impulse response of that system. That means if I take the Fourier transform of h of n, that gives me h of omega. So that h of omega is nothing but we call the frequency response of the system. Are you getting my point? So that means how the system is going to behave with the frequency. If I go on increasing or decreasing of the frequency of the input signal, then how the system is going to behave. Okay, that we can analyze or understood. So if I take the Fourier transform of the impulse response of the system, that means Fourier transform of h of n or h of t. Okay, h of t is the impulse response of the system, right? So that's why frequency response or the behavior of the system with its frequency, okay, it can be analyzed by taking the Fourier transform of its impulse response. Okay, and this h of omega, which is nothing but we call the Fourier transform of h of t. Okay, this h of omega is nothing but we can say this is the system behavior in frequency domain. Okay, so the system behavior in frequency domain, that means whether we are how much signal, how much frequency we are passing, how much frequency you can block, how much amplitude you can provide to frequency, how much blockage you can provide to certain kind of frequency. That analysis you can do. So this type of blocking or passing of the information or passing of the frequency of the signal, we call it is the filtering operation. Okay, so we can say the system when it represent the Fourier transform of the impulse response, that means we are going to design the filter. Okay, the system as a filter. Okay, so that means we can design a low pass filter, a high pass filter, a band pass filter, a notch filter, band reject filter. Okay, so we can pass a certain amount of frequency, then we block, then we call is the low pass filter. Then if you block on the low frequency information, then pass the high frequency information, then we call the high pass filter. So all these things can be represented very meaningful way by looking at the Fourier transform of the impulse response of the system, which is called the frequency response. Is it clear? Is it clear?
Sir.
Okay, so this is your frequency response of the system. So then this frequency response of the system can be also looked upon into two different parts. Okay, h of omega, which is nothing but the Fourier transform of the impulse response. This h of omega can be written as mod of h of omega into angle of h of omega. Okay, so that means we can say the frequency response it constituents of two different component. One is called your magnitude response, and another is called your phase response. Okay, and we have already discussed in the Fourier analysis. That means every signal when you represent in Fourier domain, so we can look at its magnitude spectrum and phase spectrum. Okay, so similarly, when you take the Fourier transform of the impulse response, so it will have some magnitude spectrum and phase spectrum. Okay, so its magnitude spectrum is nothing but how much magnitude or what will be the magnitude of the frequency response of the system. Okay, and when you say phase spectrum, so that means it is the how much phase shift it can provide to the signal. Okay, so how much phase it can provide, how much phase shift can be provided to the signal, and when looking at the magnitude part, then you can say how much magnitude it can multiply the input signal, or how much magnitude it can block the signal. So when magnitude is 0, we say it will block the signal. When we say magnitude is 1, so we say it is a pass the signal. So based on the frequency, so how much frequency we can multiply by 1, how much frequency we are multiplying by 0, So that is the magnitude response of the system. Okay, so combining these two, we call is the frequency response of the LTI system, or is the filter operation. This is very important concept, and for signal and system point of view. Is it clear? Or you have any doubt?
Yes, sir.
Okay, so this is some of the properties of the some of the concept of the Fourier transform that we discussed now. So we'll stop our discussion over here because further we cannot move without actually like writing in the PPT form. So verbally it not be better to discuss the next sections of the Fourier transform. So we'll close our discussion over here. So we'll meet in the next class. Okay, for looking at some other component of the Fourier transform. Okay. Is it clear?